Okay, I want to do a few examples of limits at infinity. So you have a couple extra examples to look at. So let's start with this limit. We're going to compute the limit as x goes to infinity of 2x cubed plus 3x plus 1 all over 5x cubed plus 4x squared plus 2. So the good news is that all of the limit rules that you already know apply. We can't actually use the basic limit laws here and just kind of plug in, because if we were to plug in, we would get infinity over infinity. Okay, and that's an indeterminate form, right, as we learned a while ago. So what that tells us is we have to use algebraic manipulations. Okay. With limits at infinity, when we have a rational function like this, a polynomial divided by another polynomial, there's one very particular kind of algebraic manipulation we do, and that is to factor out a common power of x from the numerator and denominator. If you always factor out the largest power of x in the denominator, I don't think you'll ever go wrong. So in this case, the largest power of x in the denominator is x cubed, so we're going to try to factor out an x cubed from both numerator and denominator. So if you do that in the numerator, you'll get 2 plus 3 over x squared plus 1 over x cubed. And in the denominator, if we factor out an x cubed, we'll get 5 plus 4 over x plus 2 over x cubed. Okay, and so now these common factors, x cubed, cancel. So we get that this is equal to the limit as x goes to infinity of 2 plus 3 over x squared plus 1 over x cubed all over 5 plus 4 over x plus 2 over x cubed. And now if we look at this, we can try doing our plugging in or using the basic limit laws. Each of the terms, 3 over x squared, 1 over x cubed, 4 over x, and 2 over x cubed, those all go to 0. Maybe I can do this in a different color. So we see that when we plug into this limit, each of those pieces with a denominator of x, those all go to 0 as x gets very large. So we get left with just 2 over 5. Okay. So now let's look at another example, one that's a little bit more complicated, where the numerator or denominator might not be a polynomial. Okay, so here's our example. So now we're going to compute this limit as x goes to infinity of x squared plus 1 over the square root of 3x to the 4th plus 7. So we're in a similar situation where the numerator is a polynomial, but the denominator is maybe a square root of a polynomial. And here we're going to take advantage of, we're going to basically do the same trick, but we're going to take advantage of what we know about square roots. So what we want to do is we want to factor out, again, the largest power of x in the denominator. If we ignore the square root, that would be x to the 4th, we can't forget that we have a square root there. So again, we're using algebraic manipulations. Since plugging in would give us infinity over infinity. Okay, and so the algebraic manipulations we're going to do here, well, we're going to try to pull out the largest power of x we can from the denominator. So that's going to be an x to the fourth, but we can't forget that there's a square root. And that'll give us a 3 plus 7 over x to the fourth. Okay, and let's just leave the numerator as it is for now. Now the square root of x to the fourth, that's x squared. So let's factor out the same factor from the numerator. We want to factor out an x squared so that these terms will cancel. Okay. So now the x squareds cancel. That was from our doing algebraic manipulations, right? Usually when we do algebraic manipulations, we like things to cancel. Okay, so now we are left with the limit as x goes to infinity of 1 plus 1 over x squared over the square root of 3 plus 7 over x to the fourth. Now again, if we now take the limits using the basic limit law, so we take the limits of each of these pieces, well, the 1 over x squared will go to 0, and the 7 over x to the fourth will also go to 0. So we're left with 1 over the square root of 3. You could rationalize this if you want to be root 3 over 3, but if you don't, that's okay too. Okay, so again, the procedure here, even though there's a square root, was similar. We wanted to factor out a large power of x, a large enough power of x from the denominator, so that when we took the limit as x goes to infinity of the denominator, we just got a number, right? We just got the square root of 3. And all the other pieces went to 0 because they had x's in the denominator. So we factored out enough x's so that we would have a constant term. Okay, so let's do one more example. Okay, so in this example, I want to show you what happens when the numerator and denominator might not have the same degree. So you can see here, we're back to the situation where we have a polynomial divided by another polynomial, no square roots or anything. Although this same sort of idea would work if you had square roots. But now you see that the numerator has degree 2 and the denominator has degree 3. Okay, so like before, if we were to plug in, we would get infinity over infinity. So we're going to have to try algebraic manipulations again. Okay, so again, we're going to use the same tricks that we were using before. So I said, let's factor out the largest power of x that we can from the denominator, which would be an x cubed. Okay. Now if we want to cancel that x cubed, we should also factor an x cubed out from the numerator. Oops, that was -1. So now these x cubes cancel, and we can again think about plugging in. Now, all of these terms with x's in the denominator, 1 over x, 2 over x squared, 1 over x cubed, 2 over x cubed, 5 over x squared, as x gets very large, all of those fractions will get very small and will all go to 0. So we see that if we plug in, or really, technically speaking, I'm putting plugging in quotation marks because we're really taking the limits of each of these pieces. So if we take the limits of each of those pieces, we'll get 0 over 3. Now that's not an indeterminate form, right? 0 divided by 3 is just 0. Okay, so we find that this limit is equal to 0. In general, what you're going to see is that if the denominator has a bigger degree than the numerator, your limit will be 0. If the numerator has a bigger degree than your limit will be infinite. And if they have the same degree, then you'll just get a ratio of those leading coefficients. Okay, so I hope this was helpful, and let me know if you have questions.